Hi, everybody. And I'd like to thank you all for being here on a Friday evening for this seminar to listen to me talk about some of my favorite galaxies in galaxy clusters. As it's been mentioned, my name is Mpati Ramatsoku. I'm from Rhodes University, as well as INAF in Cagliari, Sardinia. I'd also like to thank the organizers for inviting me to give this talk. It took quite a few attempts to actually get me here. So I'm really happy to be giving this talk today. I was told that the audience that I'll be talking to is mixed. So I'll start the talk with a few introductory slides on why we like studying galaxies in galaxy clusters. And then I will move on to my favorite kinds of galaxies, which are the long-tailed, or as we like to call them, the jellyfish galaxies. So I'll start with the kind of a mandatory slide when you're talking about galaxy clusters, especially if you are talking to people who don't work with galaxy clusters a lot. The most famous line that we use at every conference and every talk is that galaxy clusters are ideal laboratories to study environmental effects on galaxies. If you want to understand how galaxies evolve within the different environments. And as boring as this line is, it's actually true. Because even within the simple galaxy cluster environment itself, you get different sub-environments, if you will. You have the central parts, which host the BCG, and the hot intra-cluster medium, the hot plasma, called the ICM. You have subgroups falling in where galaxies tend to interact via gravitational interactions. And you have a lot of random motions, galaxies going around the center and falling in and going out of the center, et cetera, et cetera. And during these kinds of motions, galaxies tend to undergo a number of mechanisms that affect their gas composition or their star composition, or both in some cases. In this slide, for example, in the background, I'm showing a real galaxy cluster. This is Abell 2744. This is an image I got from the ESO webpage yesterday, actually. The purple hue in the background that you're seeing is all the X-ray emission that is in the cluster. In the center, you see a more concentrated X-ray emission. This forms part of the hot plasma, the ICM. And sort of around it, you see all these other sub-emissions of X-ray, if you will. And these are sort of the groups or the sub-environments within this galaxy cluster. I mentioned that galaxies tend to go through a lot while they randomly interact with the clusters and each other in this kind of field. And this is my favorite illustration by Ari Chang. I use it all the time. I love it because it explains quite well in a rather rudimentary way what galaxies can go through. These are obviously not real galaxies, but within the cluster environment, you get interactions such as harassment, where you have small little galaxies sort of orbiting a larger galaxy, therefore stripping its gas or removing its gas. You get things like thermal evaporation, and this mostly occurs. So thermal evaporation and starvation. This mostly occurs when you're very close to the ice or the center of the ICM, if you will. And so the hot plasma sort of evaporates the gas, and this mostly affects the gas of the galaxy. And due to this, the galaxy loses its ingredient to form stars and sort of become quenched, if you will. You also get things like galaxy-galaxy interaction, where galaxies fly by each other. thus removing or perturbing the stars and the gas. But the one that I'll be focusing on today is the REM pressure stripping event. This, we believe, is the most dominant mechanism that changes galaxies, or that transforms galaxies within galaxy clusters. And I will go more into a bit of details in the next slide. I forgot to mention when I was, earlier, that if you have any questions or you have something that you want to ask right away, please feel free to interrupt me at any moment and we can discuss it right away, because I'm not checking the chats. So to go into a little bit more details of what REM pressure stripping is, I'm going to use another illustration by Cameron Yosen, who I think is still at ICRA, I'm not sure, to try and explain it. So soon after a galaxy has formed, it's growing in size, of course, acquiring gas and making stars, and it's blue. It's a late-type galaxy, much like the galaxy that we live in, which is a late-type galaxy. And while it's orbiting within the cluster, the gravitational attraction of the galaxy cluster will pull it towards the center, where you have the ICM that I mentioned in the previous slide. At some point, if this gravitational attraction of the galaxy overwhelms the restoring force of the galaxy, so the galaxy's gravitational potential to hold on to its gas, this gas will be pushed away. And this is when REM pressure stripping occurs. This will go on until eventually the galaxy falls into the cluster. It doesn't have any more of its gas, and it just becomes like a red, dead galaxy, if you will. I hate using that word. We think this is the most efficient method of stripping gas in galaxy clusters. This only mostly affects the gas shell component of galaxies, and it's key if we want to understand the evolution of galaxies in these dense galaxy clusters. So, like I mentioned, I will be mostly focusing on number 2, the second panel in this illustration, where a galaxy has been is being stripped, so its restoring force is no longer able to hold on to its gas, and it forms some of my favorite galaxies, which we call the Jellyfish Galaxies, which is something I work on a lot of the times. The Jellyfish Galaxies, or the long-tailed galaxies, have this tentacle of stripped material that has been stripped from the galaxy body, and that's why they're called Jellyfish Galaxies. We believe that these represent an extreme form of REM pressure stripping. They've been predicted theoretically and were expected from numerical simulations, but have been rarely observed. Here I'm showing an example of a few jellyfish galaxies that we know of. The most famous, or the most well-known one, is the one in the Norma cluster, which has a 20 kiloparsec tail in H alpha, as is shown in this image over here from a paper from a long time ago in 2014. There's also a jellyfish in the Coma cluster, which is a very huge galaxy cluster. Actually, the Coma cluster and the Norma cluster are very huge galaxy clusters of masses 10 to the 15, so they're quite comparable. And here we also see this huge H alpha tail in a galaxy called D100. Surprisingly, there have been tails seen in early type galaxies like that found in Abell 2670, such as this one over here. We think the reason they're so rarely observed is because This stage of the galaxy requires a shorter time event. So about 10 to the 8 solar masses. We think it lasts for about 10 to the 8 years, not solar masses, excuse me. And this is basically the fraction of the crossing time. So this is the fraction of the time it takes for a galaxy to go from one side of a galaxy cluster to the other side of a galaxy cluster. This is what referred to as the crossing time. And apparently to produce these type of tails, you need really extreme environments. And so up until a few years ago, there really had been very few of these galaxies observed in nature, if you will. And this is why a project was started. The project is called the Gas Stripping Phenomenon Survey, which was conducted with MUSE. The aim of the project was to try and find as many of these jellyfish or long-tailed galaxies as could be found in galaxy clusters nearby, so we can study them in detail. So between 0.04 and 0.07, this is a survey led by Bianca Poggianti at the University of Padua, in Italy. The survey had targeted galaxies with stellar masses between 10 to the 9 and 10 to the 11.5 solar masses, so large-ish galaxy clusters. In this atlas over here, it's an atlas made by Mako. You see a wide range of these long-tailed galaxies. This one, which particularly looks like a jellyfish to me. This one over here, which looks like a jellyfish coming towards you, and so on and so forth. These galaxies were observed with MUSE, and it was found that most of them actually, the gas in the tail that is seen is ionized. And we are talking about long tails here. These tails of debris, if you will, are about 90 kiloparsecs in length. If you want to conceptualize that, this is about 3 times the diameter of our galaxy, 3 times the diameter of the Milky Way. So we are talking huge, long tails. And for us, this is what we consider a jellyfish galaxies. I say for us, within the collaboration of guests, because there have been a lot of use of the name jellyfish galaxies for any galaxy that has a tail. But within the gas content, we are talking about really, really long tails, because not all galaxies that have long tails are jellyfish galaxies, in our opinion. This is something we're still trying to fix because it's not out there in the community. In any case, the gas in these tails is ionized, and in most cases, this is due to young massive stars forming within these tails. So if there are young massive stars forming within the tails, we wanted to find out whether there could be core gas fueling star formation in these tails. So it's just a little bit unexpected. So here I'll talk about just a few selected jellyfish galaxies from GASP. This is J206 and J201. You don't have to remember those names. Just know that these are the few galaxies that I'll be talking about today. In this plot over here, I'm showing what is called the phase space diagram. This on the y-axis shows the galaxy velocity relative to that of the galaxy cluster. And on the x-axis, this is the projected distance from the galaxy cluster center to the galaxy outskirts. And this is just the escape velocity. And what we have seen is that with these jellyfish galaxies, the ones I actually showed in the previous slide, the specific ones that I'll be talking about, These galaxy clusters are caught when they're first infalling into the galaxy cluster. And so we are catching them when the galaxy stripping fireworks begin. So this is right when they start falling, and then we see these huge plumes of these long 90 kiloparsec tails. And I mentioned that the H alpha that we are seeing in the tail, we have found that most of it is due to very young recent stars that have been formed. And so when we look at the star formation history, so for example, in these panels over here, for example, the top right, starting from the top to the bottom, this is the past and this is the future. And here, from the left to the right, the past is on the left and the now is on the right. So time moves this way to this way and this way and this way. And what we are finding is that we see very young stars forming at all times. So in the past, there were stars forming within the disk of the galaxies, and as the tail formed, there were still stars forming within the tails. And you see a similar thing with this galaxy over here, which is J201, where yes, in the past, most of the stars were forming within the disk. And as you move into the now, you see that there are still young stars forming both within the disk and in the tail. So as I mentioned before, if you are seeing young stars forming, you know that there must be gas or cold gas fueling star formation. This is because cold gas in the form of H1 and CO are the main ingredients that you need to form stars. They're not the only ingredients. You need dust and a whole lot of other things to happen, but without coal gas, you cannot form stars. That's basic. And so there must have been H1 within the tail and the disks of these galaxies. However, until recently, there really wasn't any H1 available for any of the galaxies that I showed you in the previous slides. I mean, I showed you an atlas with many jellyfish galaxies, but there was no H1. H1 is very expensive and it takes a lot of time, especially if you want to be able to detect the extraplanar H1, which is found at very low surface brightnesses. In any case, so we went ahead and observed about 5 jellyfish galaxies with the VLA in its CRA. So we have the long baselines to detect. So we have the compact baselines to detect the diffuse extraplanar H1. And for each galaxies, we required about 20 hours. This is what I mean by it being very expensive to be able to observe these galaxies. We wanted to be able to reach column density sensitivity, H1 column density sensitivities of 3 × 10⁻⁹ atoms per square meters at 3 times the noise level. This is assuming that you have a galaxy of a line width of 30 kilometers per second. So this is like your dwarf galaxies per se. This column density, this H1 column density is where you want to be if you want to detect stripped extraplanar H1. And if you want to sort of conceptualize how deep you have to go to detect this, you could think of it in optical surface brightnesses. This is about an order of magnitude or so below that of a normal galaxy or a normal optical galaxy that you would see. So if you compare this H1 column density sensitivity and the optical surface brightness, say in blue, this would be about an order of magnitude below that. For a galaxy to start forming stars, we require a critical H1 column density of around 10 × 10⁻20 atoms per square centimeters. This once again gives you a conceptual idea of how deep you have to go to detect this. I really need to drive that home. we reduced all these data with Caracal. And this is a new data reduction pipeline that's in the works, and it has been public for a while. And I could not miss the opportunity to advertise it because it's working really, really well. And it has lots of people behind it working really, really hard to get it into a proper state for everybody to use easily. Now, what we wanted to do with these data was to be able to understand exactly the impact of the RAM pressure stripping event on the neutral ISM, so on the H1 and on the H1 gas of the galaxy, excuse me, and to understand the relationship between this neutral ISM and the star formation activity of these galaxies. Out of all the 5 galaxies that we were able to observe, I think we're only able to get usable data for only 3-ish of the galaxies. The other 2 had extreme absorption features in the center due to AGN activities, and so we couldn't really study them in detail. So these are the galaxies I'll be talking about in a little bit. In this slide over here, I am now showing the H1 column density contours shown in blue. These are overlaid over the V-band images of Omega Cam. This is from the VLT, the Very Large Telescope. And the different arrows are showing you the direction in which the galaxies are falling. So this galaxy over here is experiencing RAM pressure stripping within the plane of the sky, whereas this galaxy, or these 2 galaxies actually, are experiencing RAM pressure stripping within the plane of the sky. And this galaxy over here is experiencing RAM pressure stripping along the line of sight. So you can think of it as falling towards you. And so the tail is in the line of sight, if you will. I should mention that this galaxy was also reobserved with meerkats during the previous open time, 2020, I think, and the paper on this is in review, actually. And so what we're seeing in all of these cases is that there's an offset between the peak H1 and the optical center, as well as a one-sided compression. And if you were seeing these things, if you're looking at an image where H1 contours have been overlaid over an optical image, and you see that there's a one-sided compression, and you see an offset between the peak H1 and the optical center, and right away, those are the hallmarks of RAM pressure stripping. So we already knew that these galaxies were undergoing RAM pressure stripping, but we wanted to be sure that this is happening as well in H1. We couldn't just assume. I forgot to mention to you that the black contours and the red contours here indicate the optical disk of the galaxies as determined from the V band. What we found was that although these galaxies are undergoing this extreme RAM pressure stripping event, they still retain a lot of their H1 mass. So all of these actually have H1 masses of around 10 to the 9 solar masses, which is a lot of H1 mass, actually. So they still retain a lot of their H1 mass, perhaps because we're catching them right when pressure stripping is occurring, like I mentioned earlier. And so now that we know that they have this H1 mass, we wanted to see how it compares with the other galaxies of similar types, right? So in this plot over here, I'm showing the H1 fraction, which is H1 over stellar mass, as a function of the stellar mass. The gray lines is the stacked H1 scaling relations from Brown and others in the paper from 2015. Here they use, I think, alpha images, alpha data. And I selected galaxies that had the same surface stellar density as these two galaxies over here, 201 and 206. Remember, these are the galaxies I told you that I'll be talking about mostly. And what we find is that if you compare these two galaxies with the control sample is that of alpha galaxies, which are galaxies that are sitting in the field, doing nothing, just evolving secularly, basically. What we find is that these galaxies lie below the average H1 fraction that you would expect for galaxies of their stellar mass. In fact, we find that they're about 0.3 dex. Just forget about the dex, just know that they are between 30 to 50% H1 deficient. So they have 50% less H1 than we would expect for galaxies of their size. Here, we wanted to find out how much of the H1 has actually been displaced from the H1 disk. But before we could do that, we needed to model what the H1 would have looked like if it was intact in a disk. So imagine that this galaxy is sitting in the field somewhere, doing nothing, just evolving naturally. If it had the mass that we measured of 10 to the 9, what would the disk, the H1 disk, look like? And this is what I'm showing in red. So it's just a simple model that we worked out. And what we found out was that compared to what the disk would have looked like if it was sitting in nature, about 50% of the remaining H1 gas is actually also displaced. So you have this 50%-ish H1 deficiency, but then of the remaining 50% of the gas, 50% of that has been displaced from where it would have been if this galaxy was naturally sitting somewhere in the universe, not interacting with the galaxy cluster. So this is interesting. Now we wanted to find out what the relationship was between the H1 and the star formation activity of this gas, which is what the talk was originally about. And here I'm plotting the star formation rate as a function of the H1 mass. The galaxies plotted in gray, galaxies taken from a control sample. The control sample is from the X-gas survey, which is a huge survey that has H1 masses, star formation, CO, and all kinds of parameters taken from the alpha as well, I believe. These galaxies, the ones in gray, are galaxies that have stellar masses similar to those of J201 and J206. So these control samples were selected for galaxies with similar stellar masses. And what we found was that these long-tailed galaxies, or the jellyfish galaxies, tend to lie above the average population of galaxies. So they appear, at first glance, they appear to have an enhanced star formation activity if you compare this to the amount of H1.
Yes, correct.
So what we're finding is that the two galaxies lie above the general population of galaxies of similar stellar masses. And once again, there's seemed to be some form of enhanced star formation activity for the amount of H1 that these galaxies have. And here we're talking the entire galaxy, right? So this is a global observation of the entire galaxy. We find that the H1 depletion time to form these stars is around 0.2 to 0.5 gigayears. The H1 depletion time is the time it would take for galaxies to well, basically deplete its H1 if it's forming stars at a certain rate. And for these galaxies, we have very, very short H1 depletion times, which means they're rapidly using the H1 to form stars. Normally, a normal disk galaxy would take 2 gigayears, for example, to deplete all of H1 to form stars. But this is not what we're seeing in these galaxies. So there seems to be like a rapid H1 consumption that is perhaps going into forming these stars. But this, I mean, this doesn't mean much if you're looking at the global scale, because this high star formation rate could only be coming from the H1 disk. So what we also did was to look at these galaxies at resolved scales. Here I'm plotting the same, basically, but we are now separating the disk, which is in blue, and the tail, which is in red. And what we are seeing is that this enhanced star formation activity compared to the control is the disks of the control sample in the blue contours, and the disks and the tails of the control sample in red. And what we're seeing is that both for the inner and outer region, there's a relatively higher star formation efficiency compared to the filled galaxies. And in fact, the star formation activity that we're seeing would be expected if these galaxies had 10 times their current H1 mass. So something is happening here. We don't know what it is. Check the time. Okay, I have to move a little bit faster. And you might be asking yourself, okay, well, that's well and good, but you still haven't spoken about molecular gas. After all, galaxies form from the dense molecular gas, which is fueled by H1. So then we ask the same questions. What is the impact of ram pressure stripping on molecular gas? What's the relationship then between molecular gas and star formation activity? And once again, we look at the same galaxies, because we only have a sample of 5 galaxies for which we have both molecular gas and H1. These are the same galaxies I showed in the previous slide. And what we're finding is that a CO is only slightly displaced from the galaxy center. So it doesn't seem to have been moved much from the galaxy cluster center. And this is seen in these images over here. Here I'm showing CO over H alpha, and here I'm seeing CO over H1. So we see this clumpy CO in the tails that are co-spatial with H alpha. So it seems that with the CO, there's also star formation happening, and you see this in both cases. So there's always some coincidence. Well, there seems to be coincidence between CO and H1, but this is not always the case, because, for example, in this extreme jellyfish galaxy that we have over here, we don't see any CO in the tail, only H1 and H alpha. I think one of the reasons we don't have CO in this tail is because we're using ALMA data, for which we didn't have short spacing. We're still trying to get data for that. So it would appear that the molecular gas that we see in the tails is formed in situ, probably from the H1 that's been removed or that's been stripped, right? But the strange thing is, when we look at the depletion times, we find that there's a lot of CO, but the depletion times are much, much longer than we would expect. So we're seeing CO depletion times of 2 to 6 gigayears. So when we ignore H1 and we only look at CO, these galaxies seem to have lower star formation efficiency. So what is going on? And this is seen in this example over here. This is ISO 137001, and this is J100, where if you compare the star formation rate and the total H1 and H12, this galaxy seems to just be normal, basically. They look like any other galaxy sitting out there in the universe. And once again, when we look at the H2 fraction as a function of stellar mass, instead of lying below it, like we saw with H1, they lie above the H1 fraction. But when we combine the two, so when we now combine H1 and H2 fraction, they seem to be like any other normal galaxy. Once again, we're using X-gas for all the control sample. So instead of an enhanced star formation activity, there seems to be evidence maybe for enhanced H1 to H2 conversion, which is what we didn't think was before. But I mean, what could be causing this? You might be asking yourself, if H1 is so is at such low column densities, meaning it's fluffy, why is it that this fluffy H1 isn't immediately ionized by the hot ICM or lost to the ICM, for example? And this is where we started looking or experimenting with magnetic fields, if you will. We took one of the galaxy clusters, got some VLA data. This is the work that's done by Ankla, or that's done by Muller et al. And the paper has actually been accepted now, so you can go and have a look at it. And what we found was that there were magnetic fields running from the disk all the way to the tail. So what we think could be happening here is that there could be shielding. So the gas is prevented from evaporating into the ICM due to the protection that it gets from the magnetic fields. Of course, this is only based on one galaxy, and we are going to be submitting, not submitted, we tried it last time, we're going to be submitting again a proposal to get more polarization data from MeerKAT. So just running out of time. Okay, so just a quick summary. We examined the H1 gas phase of long-tailed galaxies to study their content, and we find that most of them retain their H1, and about half of the H1 that's been retained, half of that is in the tailed. They have abundant CO content, which we think formed in situ from the stripped H1, because we don't see any H1 having been moved from the galaxy disks. They have enhanced star formation activity for the amount of H1 that's detected. And we see this not only globally when we look at the entire galaxy, but at resolved scales as well. But however, when we turn this around and we look at the star formation efficiency for the amount of H2, we see the opposite, basically. So what could be happening here is that instead of RAM pressure enhancing star formation amount of H1, it could be that RAM pressure enhances the H1 to H2 conversion, and magnetic fields might be shielding the H1 from the ICM, but we don't know for sure yet. We only have a few galaxies that we've been able to play around with. There's a little bit more, actually. I told you that we only had 5 galaxies that five long-tailed galaxies for which we had H1 data, but recently, thanks to the MGCLs catalog, this is the MeerKAT Galaxy Legacy Survey, which I think all of you know, we found that there were galaxy clusters which overlapped with omega wings clusters. And within those clusters, which are listed here, so this is a variety of clusters with the different environments, we were able to find 12 more jellyfish galaxies. So this is exciting because now our sample has just gone from 5-ish, 3 to 5-ish, to now 12 more jellyfish galaxies. Now we can really ramp up these studies. And so far, we have found similar trends to what we see with those 3 or 2 that I showed you earlier. They have a lot of H1 mass, and they show these REM pressure stripping hallmarks. In these plots here, I'm showing again the V-band images with the meerkat. Now the meerkat H1 column density is overlaid at the same 3 × 10⁹ column density levels. And once again, when we look at H alpha, we see similar things. There's a coincidence between H alpha and H1. Of course, here the spatial resolution is killing us. But trust me when I say, when we convolve H alpha to the spatial resolution of meerkat, then we see nice coincidences between these galaxies. And so we did just a quick look at where most of these galaxies lie. Once again, I'm showing the control sample, which is from X gas in orange. And this is the scaling relation from, I think, brown still. And what we see is that, once again, all of the long-tailed galaxies lie below the scaling relation. So they are H1 deficient. So they're about 0.4 deaths below it. So for lower H1 content, you get a decreased H1 content with increase in stellar mass. And once again, when we look at the H1 depletion times, all of the galaxies, all the jellyfish galaxies, the ones in blue, are above, or most of them are above the general population. But this still doesn't quite answer our questions of what could be happening. Are these galaxies, instead of having enhanced star formation, are they just losing H1 instead? So we looked at what we now like to call the offset plot. In this plot, I'm showing the difference between the star formation rate that we observe and the star formation rate main sequence. So this is the star formation rate where we find most galaxies that live in the field. So if this was a perfect sample, all the galaxies will just be lying here in the middle. And on the x-axis, I'm showing the difference between the H1 fraction that we measure for these jellyfish galaxies and the H1 fraction that we expect from the scaling relations that I showed in the previous slide. And once again, I will repeat, in a normal universe where we have complete and great data, all the galaxies will just lie here in the center. Well, the majority of them do. And what we find is that indeed, for H1, lots of the long-tailed galaxies lie in this quadrant, the first quadrant here, which we call the H1 poor high star formation rate quadrant. So it would appear that indeed these jellyfish or long-tailed galaxies are H1 poor, but somehow have higher star formation rate. Again, for the amount of H1 they have. But we still don't have CO data for this. So we think that once we add in CO data, we're getting apex data for this, which is already in the process of being reduced. We think that once we have this apex data, these galaxies will move from this quadrant and sort of lie here with the rest of the population. We don't know yet. But not just to wrap up for real, summary 2.0, and some of the remaining questions that we still have. If the column density in the tails is so low, how is it that star formation activity is happening? I mentioned earlier that you need a critical H1 density of 10⁻20 to start forming stars. So how is it still happening? Maybe this is where magnetic field shielding comes into place, but so far we only have one galaxy, and we are trying to get more with the combination of meerkat and the VLA to test this. And we find that the extreme jellyfish galaxies in ionized gas are H1 deficient. Why is this the case? Maybe it's that they have rapidly used their H1 to somehow rapidly form stars. And we think that the jellyfish galaxies or the long-tail galaxies that have been identified optically are those that are now in the advanced state of REM pressure stripping, or like an extreme state of REM pressure stripping. One thing that we would like to do is to select candidate galaxies from H1 morphology and actually try to capture the initial stages of REM pressure stripping, to try and sort of find out when a galaxy becomes a jellyfish, if you will. One thing we still don't know is what are the timescales for conversion of H1 to H2? How long does it take then to convert H1 to H2? It must be short, because clearly this is occurring such that H1 is used into H2 and then immediately you form stars. So we want to understand how this relates to the general ISM conditions of the galaxies, and we think here simulations might be able to help. And as I mentioned, we are getting more CO data. Very excited about that. And we hope that we'll get more magnetic field data for these galaxies to test this hypothesis of magnetic field shielding. And I'm running out of time, so this is where I will stop for now. Thank you very much for listening.
Thank you, Mpati, for a very enlightening talk on jellyfish galaxies. Do we have any questions from the audience?
So Mpati, yeah, thanks for the great talk. It's very enlightening. To see what we're learning about H1 in galaxies undergoing REM pressure stripping. So the first question I have is about, there was a moment where you showed us, I think they were CO maps. Was that based on ALMA data?
This is ALMA, yes.
Yes, ALMA data. And you mentioned that the baselines, I think the primarily longer baselines were used to image the CO. Is that correct?
Yes.
What was the antenna setup?
Yes, so we basically just use the longer baselines to.
Okay. Okay.
This is why.
So the diffuse extended emission is what you're missing. Is that what you were?
Exactly.
You were saying? Okay.
Yeah.
All right.
So we need the compact, the ACA, basically.
Right.
Yeah.
Okay. Oh, okay. Makes sense.
Yeah.
So was there any attempt to apply a UV tapering, I guess, with the existing measurement sets that could enhance maybe? No, I don't think it's actually possible then, because you really do just need the compact baseline, the 7-meter baselines, because even if you apply the tapering on the longer baselines, it wouldn't help you much, because the antenna setup. Yeah. Okay.
Yeah, we really need ACA for this, but it's so difficult to get ACA data.
ALMA overprescribed.
So we tried again last week with the open time. So we'll see. We'll keep trying.
Yes. And which J transitions of CO are represented there?
This is 1 to 0.
1 to 0. Okay. Yeah. All right. Thank you so much. Great talk.
Thank you.
Yes. No, thanks for the excellent presentation. You talk about the REM pressure. What does REM means?
Well, REM pressure, it's not an acronym, actually. It's just like pressure that you get when you so imagine you are swimming in an ocean of honey, right? And you're trying to swim against the current of honey. The pressure that will be applied by the honey is what we call REM pressure stripping, REM pressure.
Yeah, is RAM pressure from a viscous fluid then?
Yeah, we could think of it like that, from the hot plasma. So it's the density of the hot plasma as multiplied by the velocity at which the galaxy is falling squared.
Okay, thank you, Mpati, for your talk and for attending. And thanks everybody else for attending.